Hello friends. So today we are going to look at the sixth section of the third chapter, which involves the field of quotients of an integral domain. So it all starts with this concrete case. We know that the ring of integers is contained in the field of rational numbers, right? Now the question arises, can we do this for any integral domain? Because we know that the integers form an integral domain and this is the field. So for any integral domain, can I construct a field or can I find a field in which the integral domain will sit comfortably algebraically, by which I mean that this will be a subring of F. Okay. And the answer to that question is yes, we can do and we will do that. That's the aim of this section. Okay. Now if someone asks us to describe the set of rational numbers, generally what we do, we write like this. It is defined, in fact we say it is defined as the set of quotients of integers where this, you can call it the denominator, is non-zero. Now note one thing, that because we are so familiar with these number systems that we take many of their aspects for granted. For example, we look at these rational numbers, 1 divided by 2, 2 by 4, minus 3 by minus 6, 6 by 12, and we know somehow that they are actually equal, they represent the same rational number. That means although the symbols, strictly speaking, although they look different, because they are looking different, right? The symbols that we are dealing with now, they have, each one of them has two parts, two integers, and they are looking different in each case, each of these four cases. Despite that, they represent the same rational number. So there is something here that tells us that actually, although there may be some different looking symbols, but ultimately they represent the same thing. So we have to figure this out. Okay, and figuring this out means, okay, what is the meaning of this? If I ask you, how is 1 by 2 is equal to 2 by 4? You will tell me it's because I already know it. But that's not an answer, of course. There should be a reason. And one reason that can be given is this: because this is true, because 1 times 4 is equal to 2 times 2. Then you will tell me, what is the need for writing this? Since I already know this, why do I make matters more complicated by writing yet another equivalent statement? The point here is that these symbols that we are calling rational numbers, they have been defined using the integers. So if someone is looking at them for the first time, they don't really know about these symbols, and in fact they have to be told when the symbols are equal, when we add two such symbols, what happens, how we get a third such symbol, when we multiply two such symbols, how we get a third such symbol. So those things have to be told, but in terms of what he or she already has in the system of integers. That is, this system is known, this is unknown, or it is being constructed from this system. So every condition or every definition you give to construct this system of rational numbers, that must involve only whatever you know about the system of integers. Now here the things that we have are just integers and multiplication of integers which is available to us. Okay. Now if we go to the general integral domain case, here also we want to define the field of quotients, because you see the title itself is field of quotients of integral domain. You take elements from the general integral domain where one of them you take as non-zero, and you form this quotients which, okay, now these are, do you see why this is an abstract symbol? If I just simply write this, it has no meaning by itself. It will take on meaning when I define more and more things, that is when I say what properties this symbol is supposed to satisfy, or symbols like this are supposed to satisfy. Okay. Now one such thing is this one. In this case also, similarly, analogously, if I have, say I also have C and D in D, where D is not equal to 0, I will say that two such symbols are equal if AD is equal to BC. This is meaningful in the integral domain because all it has are the elements, are some elements of the integral domain and the operation of multiplication in the integral domain. Similarly, when we add two rational numbers, say 7 by 3 plus 2 by 5, from our experience we know that this addition is just this, 7 times 5 plus 2 times 3. We will define the addition of two such symbols exactly similarly. AD plus BC. Just like that, multiplication will also be defined just like the rational numbers. And it will turn out that this much will give us a field F. But then comes another point which is in fact somewhat more subtle. Although we write that the system of integers is a subset of the system of rational numbers, in fact, we sometimes write a statement like this: every integer is a rational number. Strictly speaking, this statement is not true if someone just interprets it the way it is, because there is an extra meaning lying behind this is. This is not literally is. You see, the reason is that if I take an integer, say 2, and I ask you to show that this is a rational number, then that will amount to showing that 2 can be written as a quotient of two integers, and your answer will be this. This is quite straightforward, and you will in fact remark, why are you asking such trivial questions? Because 2 is clearly equal to 2 divided by 1. But the problem here is that, the problem again is our familiarity and experience with these number systems. We have become so accustomed to them that we have taken for granted that these two things are equal, but actually they are not equal. You see, this is a symbol which has only one component, that is an integer, and this is a symbol which has two components, they are also integers. How am I saying that those two things are equal? Actually they are not equal. Strictly speaking, they are not equal. This equality is not literal, but it is a sort of identification. The real thing is this. Here I have the field of rational numbers. Here I have the integral domain of integers, or Herstein wants to call it J, it does not matter. Now, since we already know about isomorphisms, it can be shown that there is an isomorphism from this ring into this field. Now, if you recall, isomorphism according to Herstein is an injective homomorphism. In some texts, isomorphism will the term itself will mean a bijective homomorphism, but that's not what I mean. That meaning we are not attaching to the word here. For us, an isomorphism is just an injective homomorphism. It may or may not be onto or surjective. Anyway, so since this is an injective homomorphism, there will be an image which is phi of z. Now, if we are considering this function as a function with domain z and range phi of z, then it becomes bijective naturally, because now it is surjective onto, and that automatically tells us that these two rings are isomorphic. You know from the properties of homomorphism that the homomorphic image of a ring is also a ring. So this is a ring, this is a subring of the field of rational numbers. Since these two things are isomorphic as rings, they are indistinguishable as rings. As rings, they are actually the same thing. The only difference is that their elements have been labeled with different labels. Okay, so whatever happens in one of them, the exact replica will happen in the other. So as far as ring properties are concerned, they can be considered as the same thing. They are strictly not the same thing, but they can be considered as the same thing. In this sense, the ring of integers is contained in the field of rational numbers. Actually, it is not contained, but it has a copy of itself inside the field of rational numbers, and that copy is ring theoretically indistinguishable from the ring of integers. That's why we casually write a relation like this. But when we write a relation like this, we already have in the back of our minds that this means that Q has an isomorphic copy of Z. That's what we mean. So don't fool yourself into thinking that the integers, every integer is a rational number. That is not true. And this isomorphism actually is nothing but this. The integer n is mapped onto n by 1. Okay, now since this is an isomorphism, so we do not distinguish between the input and the output. That's why we write equality. This equality is not literal equality, but it is an equality in the sense that if we if we use 2 and carry out a calculation. On the other hand, if we use 2 by 1 and carry out a similar calculation, we will end up with similar results which are ring theoretically indistinguishable. Okay, so that means a similar thing will happen here also. I mean, I want D to be a subsystem of F, but in this sense. That means I will have to find an isomorphism of D into F, and that leads to the first definition of this section, which is that of an embedding. With that, we will now start and we will see the discussion that we had here is rather informal, but when we actually construct the field from an integral domain, it will be formal and logically rigorous. So let us go with the definition of an embedding, because that's what we will need after we have constructed the field. Okay. So this is the first definition. A ring R can be embedded into a ring R prime if there is an isomorphism from R into R prime. So that is the natural definition of embedding. Okay, by the way, in this context, the mapping will be called an embedding, the isomorphism. And we will say that the first ring can be embedded into the second ring. Note that we don't need the function to be onto or anything. It may or may not be. Okay, that's not the aim. There is one additional condition. If the rings have respective unit elements then we insist additionally that the isomorphism send 1 onto 1 prime. So if the rings have unit elements, then we will call an isomorphism an embedding if it also sends the unit element of the first ring onto the unit element of the second ring. Okay, and in this context there is one more terminology. In the above definition, R prime is called an overring or extension of R. The word extension is more popular, and in fact we will devote an entire chapter on extensions of fields. We will see in 5th chapter, I think, in this book, we will study just field extensions. Now with this definition and with this knowledge, we state the only theorem, only result of this section, that is theorem 361. Every integral domain can be embedded into a field. So the statement is quite easy to understand. Now we will prove this rigorously. Okay, but there is one issue here. Since Herstein allows integral domains to be in zero ring, so that case will also come. Anyway, we will see. Proof. So we have to start with an integral domain. Let D be any integral domain. Now let us first dispose of the trivial case, namely the case where D is the zero ring. That is also an integral domain. Okay, assume D is equal to 0. So D has exactly one element. Consider the field with two elements where I don't remember whether this the example of this field has already been discussed or not when we studied examples of rings. But anyway, let us just write the operations that this field has, where I could have written it here itself. Anyway, so that's how addition works. Multiplication is also similarly 1 times 0 is equal to 0 times 0 is equal to 0, and 1 times 1 is equal to 1. One can verify that with these operations this is a field. It's not very difficult. Now the function phi from D into F given by phi of, because you see D has only one element, so I need to define only the output of that element. 0 is equal to 0. So this 0 is the 0 element in the field. Now the function can be easily seen to be an embedding. So that's how the zero integral domain can be embedded into this smallest field, the field with only two elements. Now we can assume that our integral domain is non-zero. Now assume that our integral domain is non-zero. Okay. Let us define a relation on but before defining a relation I have to define that set also. Let M be this set. It is the set of all ordered pairs of elements of the integral domain where the second coordinate is non-zero. You see here what we are actually doing is that this ordered pair has taken the role of A by B. Ordered pair is something that we already know. This symbol however is new to us in the context of a general integral domain. So this is understood. So M is the set of all ordered pairs of elements of the integral domain where the second coordinate is non-zero. Now on this set we are going to define an equivalence relation which will determine which ordered pairs are equal. That is, when these two ordered pairs are considered to be the same or equivalently, according to our previous discussion, when we have A by B is equal to C by D. Okay, so and the relation that we will define here, we have to prove that it's an equivalence relation. I can write like this. We now define a relation tilde on M as follows. For A comma B and C comma D belonging to M, we define this is related to C comma D if AD is equal to BC. Okay, so that is our definition. If AD becomes equal to BC, which is meaningful in the integral domain D, then we will say that these two ordered pairs are equivalent, or I mean related. Excuse me. We now show that this is an equivalence relation on M. Okay, so this is our first job. Okay, note that for any A comma B belonging to M, we have A comma B is related to A comma B, because AB is equal to BA. You see, these two are related. If AD is equal to BC, the outer ones are taken first and then the inner ones are taken. So we have done that same thing here. Keep in mind that we have to apply the exact definition AD, BC, BC. So AB and BA. And why is this true? This is because according to our definition, any integral domain is after all a commutative ring. So AB will be equal to BA. Hence, the relation is reflexive. Next, let belong to M such that this is related to C comma D. Then according to the definition of this relation, AD is equal to BC, which implies what do we need actually to have CD also related to AB? We need CB is equal to DA. Now do we have that, which implies CB is equal to DA? I can of course write BC is equal to AD because ordinary equality is symmetric, and in place of BC I can write CB, in place of AD I can write DA because I have commutativity in the integral domain. That this is related to A comma B. So the relation is symmetric. So what's left is transitivity. Next, let A comma B, C comma D and E comma F belong to M such that AB is related to C comma D, and this is related to E comma F. Then what do we have? AD is equal to BC. And from here we will have CF is equal to DE. For having AB related to EF, what do we need? We need AF is equal to BE. Okay.